Hi, everybody. So today we are doing a little bit of a lesson on implicit differentiation and related rates, both important calculus concepts that will help you as you enter university. Um, and it just gives you an idea of what else is out there in calculus. We're just barely scratching the surface here in grade 12. So implicit differentiation deals with relations that aren't functions that we can't define explicitly by y. So here's an example: x squared plus y squared equals 25 of a relation that if you isolate y would give two different y values for any given x. Okay, so this in and of itself here is not a function. It can be broken down into two separate functions. So like the red is the top there, and then the blue is the bottom. But if we're looking to differentiate the entire circle, we don't want to have to do two separate derivatives, one for the top and one for the bottom. So how can we figure out the derivative, the rate of change of y with respect to x, by looking at the entire function? Well, let's think about it. Like if we let x equal 3, then that would give us two different derivatives. So it would give us the one here, so you can see f prime at 3 would be negative 0.75. And you can also see g prime at 3 would be positive 0.075. So if you did a tangent, point function, so 3 on f, there you can see it, and the tangent at 3 on g, you can see it there. So this is like I said, negative, and this is positive, but how can I come up with an equation where I could find both of these derivatives without having to do them separately? So that's what we're going to do as our first example on the note. So this is a function, this cubic is a function defined explicitly as a function of x. So y is isolated. You have y equals f at x. But the relation x squared plus y squared equals 25 is not explicit. There are x values that give two y values, so this is not a function. In relations like this one, we use implicit differentiation to find dy dx. So remember, dy dx is the derivative of y with respect to x being the variable. So how we solve something like this is we set up dx squared plus y squared dx. So we're taking the derivative of the left side, and d25 dx of the right side. So we're doing the same thing to both sides. So what we're going to do first, where's my little pen here? Hello. Okay, so what we're going to do first is break this down into dx squared dx plus dy squared dx equals, you can put that in brackets if you want, d25 dx. So I just took this expression and broke it into its different parts. So let's think about what's going on here. Well, this is the derivative of x squared with respect to x, this part. So that is just 2x. And this over here is the derivative of 25 with respect to x, so a constant, and that derivative is 0. But the question is, what do we do with this middle part? Okay, the derivative of y squared with respect to x. So let's think about this. So we can say that y can be written with respect to x. So therefore, think about the chain rule. So if you were taking y, which is a function with respect to x, you would take the 2 down, you would leave y the same, and then you would multiply it by the derivative of y. So this is how we write it. Okay, so 2x plus 2y times y prime equals 0. So we can rewrite this, well, actually, you can leave it as y prime, or you can rewrite this as Leibniz notation, 2x plus 2y times dy dx equals 0. So now here is dy dx, and we just need to isolate it, and we will have an expression for it. So you can get 2y equals, 2y, sorry, 2y times dy dx equals negative 2x. I just brought that to the other side. And then dy over dx equals negative 2x over 2y. So it just equals negative x over y. So that means that the derivative at any x value is the negative x value at that point and y value at that point. So you actually have to know the y value that you want to differentiate, okay? And that's why here it's negative x, so negative 3 over the y value, which is 4. So negative 3 over 4, negative 0.75. And here it's negative 3 over negative 4, so positive 3 over 4, which is the derivative there. Okay, so let's try another example to see if you guys can understand it. This one's a little bit more complicated. Okay, so the first thing we always do is take dy dx of both sides, or of each thing individually. So we're going to take d 2xy dx minus dy cubed dx equals d 4 dx. Okay, so this derivative of the constant is 0. That's kind of the most obvious one. And then we're going to separate this into d 2x over dx times y plus, I shouldn't have put this equals 0 there. Okay, so what is this here that I'm doing? So I'm looking at this as a product rule. So I'm taking the derivative of 2x with respect to y times y plus 2x times dy dx. Okay, so what I just did here is the chain rule of this. Okay, now this, remember we think about y as a function. So we have 3y squared times dy dx. So that uses the chain rule where y is a function of x, and we let that equal 0. Okay, from here on, it's really just, mostly calculator. Okay, actually this here turns into 2, okay? Because the derivative of 2x with respect to x, that's just 2. So we get 2y plus 2x dy dx minus 3y squared dy dx equals 0. Okay, so from here I should say it's all just algebraic work. So I'm going to move this 2y over to the other side, and then I'm going to common factor out a dy dx. So dy dx bracket 2x minus 3y squared equals negative 2y. So I just move the 2y over, common factored out dy dx, and now I can isolate dy dx equals negative 2y over 2x minus 3y squared. And this is the implicit differentiation. Okay, now there is a way to do this with prime notation. So if you want to see that tomorrow, let me know. I can show it to you with, and instead of dy dx, using y prime as an example. Okay, so that's implicit differentiation. Now we're going to look at related rates, which kind of has that as an application. So again, chain rule is very important here. It's really crucial that you do understand the chain rule in order to understand these problems. So related rates are just rates that vary in relation to each other. So as one thing changes, another thing also changes. So a classic example, which we'll get to, is water filling a cone. So as the height changes, the radius is changing as well. Or in this case, a raindrop hits a puddle and there's a circular ripple. So the radius is going to grow as the area grows. Okay, so they're related rates. So this is where your Leibniz notation is actually really going to come in handy. So here, Determine the rate. So we have a radius that grows at 3 centimeters per second. So what that means is that the change in radius, so dr, with respect to the change in time, dt, is equal to 3. So that's an important interpretation that we're going to use throughout this problem. Okay, so the radius with respect to time. So determine the rate of increase of the circumference of the circle with respect to time. So what this is looking for is the change in circumference, dc, with respect to time, dc dt. Okay, so if we look at the circumference of a circle, that's 2 pi r. So notice that if we take the derivative of this, it would be just with respect to r. But r can be written as something with respect to t. So when we take dc dt, we're actually taking the derivative of the circumference with respect to the the radius. And then we're going to multiply that by the derivative of the radius with respect to time. So that is d of 2 pi r dr times 3, because we know that that is 3. So this derivative is just 2 pi because r is the variable. So we have 2 pi times 3, so we have 6 pi, and that would be in centimeters per second. So the rate of the increase of the circumference with respect to time is 6 pi. It's increasing 6 pi centimeters each second. So now let's try a different question, which asks us about the area. So it asks us about determine the rate of increase of the area of the circle when the area is 81 pi. So they want to know dA dt. Okay, so dA dt, so area is a function of radius, so we have dA dr. So then we need to multiply it by dr dt in order to get dA dt. So this is the derivative of pi r squared with respect to r times dr dt, which we know is 3. Okay, so this is just, remember, r is the variable, so you get 2 pi r, and then this is 3. So dA dt, so the area, the change in area with respect to time is 6 pi r. So it's asking us, what is dA dt when the area is 81 pi? So when the area is 81 pi, we need to find out what the radius is there. So when pi r squared is equal to 81 pi, we get that r is equal to 9. Divide both sides by pi, and then take the square root of 81. So now we're going to take that 9 and put it in here. So then the change of area with respect to time is 6 times pi times 9, which is 56 pi centimeters squared per second. Since it's the area units divided by the time units. Okay, so now let's do this classic cone example. Okay, so water is pouring into a cone at pi cubic meters per minute. So imagine, you're putting in water and it's creating circles that go up and up and up and up and up and up and up, and they're growing in size. Okay, here we have the height and the diameter are equal. So that also means that the height is going to be equal to 2 times the radius, or the radius is equal to half the height, and that's going to be important. Okay, and that's at any given point, right? Because it's in ratio with each other, this relationship is going to stay true. So how fast is the water level rising when the depth is 8 meters? So they want to know, what is dH dt when h is equal to 8? That's what they want to know. We also know that water is pouring into the cone at pi cubic meters per minute. So that is the rate of change of the volume with respect to time. So we know that that is equal to pi. So we're going to use our knowledge of this relationship to find dH dt. So right now, let's think about what we know about the volume of a cone. The volume of a cone formula is 1/3 pi r squared h. So right now, volume is a formula that involves the radius and it involves height. But because we know of this relationship here, we can change it so it is all in terms of h. So let r equal half h instead, and that will allow us to only have dH dt when we take the derivative, okay? So we want volume as a formula of height, or as a function of height. So we get 1/3 pi half squared like that, half h squared times h. So that half squared is a quarter times 1/3 is 1/12. And then h squared times h is h cubed. Okay, and now we want dH dt. Okay, so we can take the derivative of this. Okay, so we bring, so dV dt equals, so now we have to take the derivative of this with respect to h, and then multiply it by the derivative of h with respect to time, and this gives us dV dt. Now we know dV dt is equal to pi because we were given that information. This is, we bring down the 3, so we get 3/12 pi h squared times dH dt, which is what we're trying to solve for. Okay. And we also know that we want h to be 8. So now we get pi equals 1/4 instead of 3/12 pi 8 squared times dH dt. So now we can isolate dH dt. Okay, so pi divided by pi, you do all this math and you get 1/16. Okay, and sorry, that should say dH. Okay, and think about the units. So it's the units of height, which is meters, with respect to the units of time, which we were given as minutes. So when the height is 8 meters, then the height is rising at a rate of 1/16 meter every minute. Okay. Last question involves the separating distance thing. Okay, so we're going to use Pythagorean theorem here. Before we get started, I'll let you know that. But let's go ahead and read the problem. So Shannon and Natalie leave from the same point. So they're both leaving from this point, okay? Natalie drives east at 45 kilometers an hour. So here's Natalie. Okay, and Shannon drives north. So here's Shannon. So Natalie's going 45 kilometers an hour, and Shannon is going 40 kilometers an hour. So be clear, these are their rates of change, okay? So these are already rates. We'll have to get to that in a second. Shannon begins 1 hour before Natalie. We'll use that later. And at what rate are the cars separating 3 hours after Shannon leaves? So Shannon has been traveling for 3 hours. Natalie has been traveling for 2 hours. So they want to know the rate at which R is changing, the distance between Shannon and Natalie. So we can call this distance between the old point here X and this distance Y. So we can say let X represent distance Natalie has traveled. In kilometers. And let Y represent distance Shannon has traveled in kilometers, okay? So notice that we actually can already say what X and Y are because we know Natalie's been going 45 kilometers per hour for 2 hours. And we know that Shannon's been going 40 kilometers an hour for 3 hours. So we can actually figure that out, but we'll leave them as variables for right now. You'll see why. So we know from we know from Pythagorean theorem that x squared plus y squared equals r squared. So what we want, remember, is dr dt. So let's take the derivative of all of this with respect to t. So let's take dx squared with respect to t plus dy squared with respect to t and dr squared with respect to t. And just see what happens. So remember, none of these are variables involving t, so we think about this as chain rule. So we bring down the 2 x, and then we have dx dt. And then this gives us 2y times dy dt. And this gives us 2r times dr dt. So notice that this is what we want right here. This is what we want right here. So if we can fill everything else in with numbers, then we can solve for our unknown. So let's think about this. Well, dx dt, that means the change of x with respect to time. So that is actually Natalie's speed. And this dy dt, again, is a change of distance with respect to time. So this is actually just Shannon's speed. So we can actually fill those in. And we can also divide everything by 2. Okay? So everything can be divided by 2 to get rid of the 2's. So we have x times her speed is 45 plus y, and her speed is 40, equals r times dr dt. But like I said, we actually know x because that is how the distance that Natalie has gone. So Natalie has gone 2 hours at 45. So x is equal to 90. And then y, this is Shannon, right? So she's gone 3 hours at 40. So her distance is 120. And then r, well, r is just the square root because it's the radius of 90 squared plus 120 squared. So that is equal to 150 when you do that calculation. So I can plug this all in, and I get dr dt is equal to 45x plus 40y all divided by r. So that's just rearranging this formula. And then I sub in everything I know. So 45 times 90 plus 40 times 120 all over 150. And you get a result of 59. And this is kilometers per hour. So there's a neat little related rate problem for you. Okay, guys, I hope you enjoyed seeing this kind of preview of implicit differentiation and related rates. Thanks for watching. Hope you learned lots.